So I hope that my voice and video are clear. So as you all know that we are actually in the fourth lecture of the EMFT where we are discussing the basic fundamentals of EMFT which is required to start with any particular chapter. Like suppose if you want to start the electrostatic, if you are from electrical or instrumentation, then you need the delta operator conditions, coordinate systems, differential elements, differential volume, etc. Now, if suppose you want to prepare magnetostatic, or if you are a EC student, if you want to go for the plane wave propagation and the waveguide, then for that again you need a basics of coordinate system and you have to understand the del operators. If you want to prepare for antenna, then again you need a coordinate system. That is especially spherical coordinate system. So it becomes very important to have these fundamental topics very clear, and that is why I have brought this particular series in this fundamentals. GATE and ESE fundamentals. I am covering these topics just because of that reason, because this is the fundamental topic for all the other branches like EECIN. If you are from, then it is the fundamental if you want to start any main chapter. So let's start with the basic introduction that if you are not aware about myself, then this is Saket Verma and I have done MTech from IIT Guwahati and I have more than 12 year experience and I cracked a different PSU exam as well. My area of expertise are electromagnetic theory, communication system, advanced communication system, signals and system, and ICT. These are my area of expertise. So if you have any doubt in these subjects, then you can ask me. And very important if for all of you, that those who are going to prepare for GATE 24, this is the national scholarship test which we are conducting for the GATE exam, where you will get the 90% discount, up to the 90% discount on the our full course, that is our GATE 24 and GATE and ESE 24. And the date for the exam is 30th April. In this 30th April, you can go and take the scholarship test and you can get the maximum discount. So for that, you can register yourself. The link is given in the description. So don't forget to register yourself for this particular case. Now coming to the vector calculus. So there are different things that we need to understand today. That is the gradient, divergence, and curl in the different coordinate system. So what is the gradient? Gradient is nothing but the maximum rate of change per unit distance. What is the divergence? Divergence is the measure of how much a flux or electric field move outward towards any point, and curl is how much a vector field rotates about any point. So these are the basic meaning of the gradient, divergence, and curl. But before going to that, let's understand what is the del operator. So del operator is a vector quantity. We generally represent that del as a. In the Cartesian coordinate system, it is nothing but the differentiation with respect to x, y, and z. When you differentiate it, because as I said, that it is a vector quantity, you have to multiply it with the unit vector ax, ay, az. In the cylindrical coordinate system, it is a rho, a phi, and az. These are the unit vectors, and this is del upon del upon rho d phi, and del upon del z. And in case of a spherical coordinate system, it is del upon del r, and 1 upon r, del upon del theta, and 1 upon r sin theta, del upon del phi. So this is the spherical coordinate system. Okay, so this is the spherical coordinate system. Now, as I said that we are going to understand the gradient. So how do you write this gradient? So let's understand how do you write this gradient in the Cartesian coordinate system. Okay, so to write the gradient, okay, let's suppose we have the gradient. We always calculate the gradient of a scalar. Okay, suppose you are calculating a gradient, so you calculate only for a scalar. So gradient is calculated always for a scalar. First point that you should know that gradient of vector, if you say, then it is an invalid statement. Gradient of vector is invalid statement. Okay. The second thing is gradient is represented by gradient of scalar is represented by gradient. This is inverse delta operator, or and then scalar, let us suppose V, where V is scalar. Okay, now the third is gradient of scalar. Whenever you calculate the gradient, then the gradient of scalar is vector quantity. Gradient of scalar, when you calculate the gradient of a scalar, result is vector quantity. You should write like this. Okay, so these are the three things that you should know. And now to write the gradient of scalar in the different coordinate system, you should remember the differential length. As I said yesterday also, the differential length is very important to write the differential surface, differential volume, and now I am saying that it is important to write the gradient also. So this is the differential length in the Cartesian coordinate system. This is the differential length in the cylindrical coordinate system, and in the spherical coordinate system differential length is dr ar and r d theta a theta and r sine theta d phi a phi. Okay, so these are the different coefficients. So I am marking the coefficients. So look at these coefficients of the unit vectors. So the coefficients of unit vectors are this, which I have underlined. Okay. Now, when you write the gradient of a scalar, then this is del V upon del X. So you can see that in the denominator what we have? In the denominator we have the differential length coefficient. Ax is the unit vector, ay and az are the unit vector. What is the coefficient of unit vectors? Ax, ay, dx, dy and dz. So that is coming in the numerator, and in the in the denominator. In the numerator, it is the differentiation of scalar only. So it is d rho d phi and dz, and this is dr, r d theta and r sin theta d phi. All this I have boxed. That is nothing but the differential length. Dr r d theta r sin theta d phi, dr r d theta r sin theta d phi. So you can memorize in this way. You can relate them, and after relating them, you can easily write the gradient. Now, what is the significance of gradient? Gradient, whenever we calculate for a scalar, it gives you the maximum rate of change per unit distance. So, if you move any at any particular distance, how much is the change? That is the maximum rate of change it gradient defines. So, obviously, when you move from somewhere one point to another, there will be a change in the distance. So, in which direction you will move? In the maximum direction when you move as per the distance, then it becomes the gradient. Gradient gives the direction of maximum rate of change as a function of f, and gradient is also useful to calculate the directional derivative along any vector. So directional derivative of a scalar function f at some point p in the direction of a vector, in the direction of vector, is given by, this is gradient of phi. Suppose you are calculating the gradient of any function. So this is gradient of f, you can say gradient of f at the point p and dot product with the unit vector of the vector in the direction you will want to calculate the directional derivative. Suppose you want to calculate the directional derivative in the direction of vector A, then calculate the gradient of f at any point at which you want to calculate the direction derivative, and then take the dot product with the unit vector of a vector in which you want to calculate the directional derivative. Now, divergence. Coming to the divergence, divergence is having no shortcut and no particular method to memorize. You have to memorize it directly. So that is nothing but the the because you are calculating. So yes, before writing that, let's write the divergence. So divergence of a vector is always calculated. Okay. So first point, divergence of a scalar. If somebody will ask you that what is the divergence of a scalar, the divergence of a scalar is invalid statement. Okay. The second point is divergence of a vector. When you calculate divergence of a vector, results scalar quantity. Divergence of a vector results scalar quantity, and divergence of a vector. Divergence of a vector. Divergence of a vector is denoted by, suppose this is the del operator, dot product with the vector. Let us suppose the vector is E. So in this way we represent. So here we are calculating the divergence of F. So del dot F. Okay. And then that is nothing but because you are representing a vector in the Cartesian coordinate system. In the Cartesian coordinate system, vector is having a magnitude fx in the direction of x, magnitude is y in the direction of y, magnitude is z in the direction of z. So these are the coefficients. So take the coefficient of vector and differentiate with respect to x, y, and z. So differentiate with respect to x, y, and z. Similarly, the vector is f. Now this is f rho a rho plus rho sorry f phi a phi and fz az. These are the coefficients f rho, f phi, and fz. So here the formula is a bit different. 1 upon del rho, rho into f rho plus 1 upon rho del f phi upon del phi and del fz upon del z. Similarly, in the case of a spherical coordinate system, this is 1 upon r square del upon del r. After differentiating r square into fr, you have to divide. Don't think that this r square and r square will get cancelled. No, it is inside the differentiation, so it cannot be cancelled. So actually it is the 1 upon r square del upon del r in bracket r square into fr, 1 upon r sin theta del upon del theta sin theta into f j theta, f theta, and this is sin theta, 1 upon r sin theta del f phi upon del phi. So this is the formula in the divergence. Now, what is the physical significance of a divergence? Divergence is a measure of how much a field line diverges about any point. So that means if there is any point P, and if I want to calculate how much a field line is leaving the point P, then I will calculate the divergence at that point. Suppose these are the field lines which are leaving this point P, then I will calculate the divergence, and because it is leaving, the divergence of that vector A at the point P will not be equal to 0. That means it will be positive. Because it is leaving, it is positive. And suppose at the same point P, if the field line may be from any vector quantity which is placed at some distance. So the field lines are coming inside this point P. Then when you calculate the divergence at that point, then the answer will be negative. And suppose at this point P, the vector field coming inside and going out are same. That is inside, that is outside, that is inside, that is outside, that is inside, and that is outside. So here the total number of fields coming in and coming in and going out are same. So in this case, if you calculate the divergence at the point P, then the result will be 0. Okay, so that is your physical significance of divergence. Now coming to the next point related to the divergence, that is divergence theorem. So what is the divergence theorem? Let's write. It states that total flux passing through the closed surface. Okay, total flux passing through the closed surface is equal to the volume integral, sorry, is equal to the divergence of the vector is equal to divergence of the vector, or let me write in this way, is equal to the volume integral of, is equal to the volume integral of, okay, volume integral of divergence of the vector. That is integration over the closed surface d dot ds, that is representing the flux, is equal to volume integration of divergence of the vector. What is the vector? That is the d. So divergence of the vector d. Okay, so this is the divergence theorem. Now coming to the next, which is the curl. So to write the curl, again I am giving you the trick, the same trick we have to use. So let's write the curl. Curl of a vector. We always calculate the curl of a vector. So first thing that you should know about the curl. Curl of a scalar is invalid. The curl of a scalar is invalid statement. Okay. The second thing, curl of a vector results a vector quantity. Okay. So when you calculate the curl of a vector, it results the vector quantity. The third thing is curl of a vector is represented by del cross the vector A. Del cross the vector A. So these are the 3 points. And again, to write the curl, we need a differential length. So what is the differential length? In the Cartesian coordinate system, this is dx ax plus dy ay plus dz az. And what is in the cylindrical coordinate system? This is d rho a rho, then rho d phi a phi, and then dz az, and again write in the spherical coordinate system, this is r d theta a theta and r sine theta d phi a phi. Now let's underline the coefficients, that is dx, dy, dz, d rho d phi dz, and dr r d theta and r sine theta d phi. So this dx, dy, dz, let's write the curl. The curl you have to write in the form of a determinant. This is the determinant. This is ax, ay, az. These are the unit vectors. In the first row, you have to write the unit vectors. In the second row, you have to write the differentiation of with respect to x, y, and z if it is Cartesian coordinate system, and then write the vectors, coefficient of the vector, which is fx, fy, fz. So there is a very simple calculation, right? You can calculate the determinant. Now, if you want to write in the cylindrical coordinate system, then you will write in the same way. You will write a rho, a phi, and a z. Then del upon del rho, del upon del phi, del upon del z, and the coefficient f rho, f phi, and f z. Okay, first of all, write in this way. Then what is the change in the differential length? In the differential length, you have, with respect to phi, you have extra term which is rho. When you write the unit vector in the direction of phi, you have an extra term rho. So that rho is multiplied with this phi, okay, and that rho is also multiplied with the coefficient of the vector, that is f phi. So that rho is multiplied in these two, which is associated with phi. Now, if you multiply coefficient of all the three, this has the coefficient 1, this has the coefficient rho, this has the coefficient 1. This dz az is having the coefficient 1. Previously also this dz az was having the coefficient 1, dy ay was having the coefficient 1, this d phi a phi is having the coefficient rho. Multiply all the three coefficients, that is 1 into rho into 1, you will get rho. So what is the multiplication? Rho. So divide the determinant by rho, then you will get the cylindrical coordinate system curl in the cylindrical coordinate system. Similarly, in the spherical coordinate system, write the unit vectors AR, A theta, A phi, FR, coefficient of vectors FR, F theta, F phi. Now, what is the term associated with theta is R. So, multiply the coefficient which is related to theta with R. Then, with respect to phi, we have R sin theta. So, multiply with R sin theta. Now, let's multiply all the three coefficients. It has the coefficient 1, it has the coefficient R, it has the coefficient R sin theta. When you multiply all these three, this is 1 into R sin theta, which is nothing but a R square sin theta. So divide the whole determinant by R square sin theta. Now you are having the formula of curl in the spherical coordinate system. Very easy. Now coming to the significance of the curl. It is a measure of how much a vector will curl about any point. So if at about any point, if a vector is rotating, then we call it as a curl of the vector. Suppose this is the point P, and you want to calculate the curl about the point P, and if the vector is rotating in this direction, if a vector is rotating in the anti-clockwise direction, then when you calculate the curl of any vector, then you will get non-zero value. You will get non-zero value. Okay, because the vector is rotating about the point P, you will get non-zero value. Now you can say that, sir, do we get the same result when the vector is rotating in the clockwise direction? So the answer is yes. The curl of a vector is again non-zero when you calculate the curl of a vector about the point P if the vector is rotating. See, according to the rotation of a vector about the point P, the direction is changed, but the magnitude will be non-zero. Okay, the result will be non-zero, only the direction will change. When you curl your right hand, but according to the anti-clockwise direction, the thumb is pointing towards the outside the screen. Okay, when you rotate in this way, the thumb is outside the screen, and when you rotate in this direction, that is in the clockwise direction, the thumb is inside. So that is showing the direction only, but the curl is non-zero. And suppose the vector is not at all rotating about the point P, because this is a straight line, this is a straight field which is going about the point P, it is not rotating. So if it is not rotating, then the curl when you calculate at point P will come as 0. Now coming to the Stokes theorem, what it says, okay, what it says, it states that circulation of a vector around the closed loop it states that the circulation of a vector around the closed loop is equal to surface integration of curl of a vector over the open surface bounded by closed loop. So that is integration of a vector that about the closed loop, that is integration over the closed loop A dot dl. A dot dl is equal to integration over the open surface curl of the vector dot ds. Curl of a vector dot ds. So this is the Stokes theorem. Stokes theorem also gives you the relationship between the closed integral and the open surface. Now coming to the Laplacian of a scalar. So Laplacian of a scalar and vector both can be calculated. Okay, Laplacian of scalar and vector both can be calculated. First, in the Cartesian coordinate system, the Laplacian is del square into V. How do we define? Laplacian is defined as Laplacian is defined as divergence of gradient. Okay, divergence of gradient of scalar. So this will be del square V, and it is nothing but a double differentiation with respect to x, double differentiation of the scalar with respect to y, and double differentiation of a scalar with respect to z. In the cylindrical coordinate system, it is del square V, it is 1 upon rho, del upon del rho, in bracket rho into del V upon del rho, plus 1 upon rho, del upon del phi, del square upon del phi square into V, and then del square V upon del Z square. And in the spherical coordinate system, it is del square V is equal to 1 upon R square del upon del R square del V upon del R, plus 1 upon R square sin theta del upon del theta sin theta del V upon del theta, okay, plus 1 upon R square sin theta del upon del theta del square V upon del phi square. Okay, so this is your Laplacian. So this can be calculated for scalar as well as vector. So how do we calculate for a vector? So that we can see from the important points. What are the important points which you need to know, because the question will be asked from these important points mainly in the GATE examination. Okay, if you are a electrical student or an instrumentation student, the question will come from here, that a vector is said to be solenoid or divergence-less. A vector is said to be solenoid or divergence-less if the divergence of any vector is equal to 0, then you will call it as a divergence-less. So always remember that if suppose they will give you the vector which is divergence less, then equate the divergence equal to 0 of that vector, and they will ask you to calculate some constant. So the question we will do tomorrow. Now the second, a vector is said to be irrotational. Okay, a vector is said to be irrotational or conservative. A vector is said to be irrotational or conservative if the curl of a vector is 0. Suppose curl of a vector is coming 0, then it is irrotational. Okay, now the third point. A scalar is said to be harmonic. A scalar is said to be harmonic if uh, a vector is said to be harmonic in all the region if the Laplacian is 0. Laplacian of a scalar is suppose 0, then you will say that it is harmonic. Now, fourth point, divergence of curl. Divergence of curl of any vector is always equal to 0. The fifth point, curl of gradient of scalar is always equal to 0. And Laplacian of a vector is nothing but the gradient of divergence of a vector, because the divergence of a vector is a scalar quantity, and for scalar we can calculate the gradient, and that is curl of a vector. So these are the important points to solve any problem of the gate. So you should remember all these points. So this is our success saga which we are continuing since many years. And GATE 23 also we have got all India rank 50, under 50 we have got 62 rank, under 100 all India rank 10, under all India rank 10 we have got 13 students, and under all India rank 100 we have got 107 students, and these are our some students those who have got under 5 rank. Okay, so thank you for watching this session. Don't forget to subscribe the channel, and we are also running free app session, means free classes in the our app. So you can download our app from this particular link. Link is given in the description, and you can also join our Telegram group for more update about the upcoming series. And BYJU'S you can go and visit the our full course. What are the full course which we are running for the GATE 24 and GATE 20 ESE 24. Okay, thank you. Let's meet tomorrow at the same time. Good night.